In sections 10.3 and 10.4, we will talk about hypothesis testing for two means, both independent and dependent samples. Two samples are independent if the values from one population are not related or somehow naturally paired or matched with the sample values from another population. In other words, two samples are independent if the individuals selected for one sample do not dictate which individuals are to be in a second sample. To determine if a sample is independent, ask yourself this question. Are the samples from the two groups related in any sort of way? Here's an example. Researchers investigated the reliability of test assessment. One group consisted of 30 students who took a proctored test. A proctored test is when you have someone watching you. A second group of 32 students took tests online without a proctor. So if they wanted to, they could have had someone else take the test, have someone else next to them that could have helped them. The two samples are independent because the subjects were not paired or matched in any way. In other words, there was no relationship between the subjects of the two groups. Another example. Annual incomes are obtained from a random sample of 1,000 residents from Hawaii and another sample of 1,000 adults from Alaska. The two samples are independent because the subjects are not paired or matched in any way. There was no relationship between the residents of Hawaii and the residents of Alaska. Another example. To determine whether smoking affects memory, 50 randomly selected smokers are given a test of word recall, and 50 randomly selected non-smokers are given the same test. Once again, the two samples are independent because the subjects were not paired or matched in any way. In other words, there was no relationship between the smokers and non-smokers. When samples are independent might actually become more clear when we take a look at when samples are dependent. Two samples are dependent, often referred to as matched pairs, if the sample values are somehow matched, where matching is based on some inherent relationship. In other words, two samples are dependent if the individuals selected in one sample are used to determine the individuals that are selected in the second sample. So ask yourself this question. Are the samples from the two groups related in any sort of way? If they are, then they are dependent samples. Here's an example. Researchers collected the data consisting of heights of 10 randomly selected women and the heights of their husbands. Okay, so let's think about this. My wife's name is Rucha. And to be in the study, the researcher wants to select the name of the wife and her husband. So if Rucha is selected, that means I have to be selected since I'm her husband. These samples are dependent because they're matched with the heights of their wives, matched pairs. The husbands and wives are related, literally in this case. Another example, to test the effectiveness of a diet, 36 randomly selected subjects are weighed before the diet and after 6 months of treatment with the diet. The two samples are dependent since the first sample is the weight of the person before the diet and the second sample is the weight of the same person after the diet. So the same person, they're related to themselves. It's not possible to take the before weight of one person and compare it to the after weight of another person. You have to compare the before and the after weights of the same person. Therefore, the individuals that are selected in one sample, in this case, that person, is also selected in the second sample. Finally, to test the difference between the ages of actresses and actors when they win Oscars, 10 different years were randomly chosen to sample, and the ages of actors and actresses from each year were recorded. In this case, the actors and actresses are not necessarily related, however, they are selected from the same year in each case. So the year is the relationship. The actors and actresses, there is an actor and there's the actress. Because they're both selected from the same year, they are matched. Here's a hypothesis test for two independent samples. Please look over the requirements, which we will go over in class. In hypothesis test for two independent samples, the null hypothesis is always that the mean of the first sample or mean of the first population is equal to the mean of the second population. In other words, there is no difference between the two populations. The alternate hypothesis is that the mean of the first population is greater than the mean of the second population, or the mean of the first population is less than the mean of the second population, or the means of the two populations are not equal. In the case of wives and husbands, the researchers were studying the heights, the mean heights of wives and the mean heights of their husband. Typically, the height of a wife is less than the height of a husband. Typically, husbands are taller than wives. So we would expect in that case that mu1, the population mean of wives, is less than mu2, population mean of husbands. So in this case, we are comparing the two populations, the means of the two populations. So in step 1, we write the null and the alternate hypothesis. In step 2, we calculate the test statistic. In this case, we will use technology. We will not be using the formula at all. Using technology, we will also calculate the p-value. And then finally, we will write a conclusion sentence. Here's an example. Let's go back to the example of the proctored tests. One group consisted of 30 students who took proctored tests, which means they were being watched by someone. A second group consisted of 32 students who took tests online without a proctor, which means they could have had someone to help them, or someone else could have taken the test for them. The two samples were taken independently of each other since there's no relationship between the first and second samples. Assume the conditions for inference procedure are met. Use a 0.01 level of significance to test if the non-proctored group is significantly higher than the proctored group. So, is the mean score of the non-proctored group significantly higher than the mean score of the proctored group? Since the non-proctored group could potentially cheat, are their scores significantly higher than those of the proctored group? So group 1 is a proctored group, and this is their data. Group 2 is a non-proctored group, and this is their data. So let's write our null hypothesis. Our null hypothesis is always that the means of the two populations are equal, which means there is no difference between the scores of the mean scores of the proctored or non-proctored. So whether a group is proctored or not makes no difference in their test scores. Alternate hypothesis is what we're testing. We're testing to see if the non-proctored group is significantly higher than the proctored group. Here's a dilemma though. Group 1 in this case, mu1 is a proctored group and mu2 is a non-proctored group. We want to test is the mean scored of the non-proctored group, which is mu2, greater than the mean scored of the proctored group, mu1. However, we need to write mu1 first for the purposes of our alternate hypothesis. So let's flip this inequality around and write mu1 less than mu2. In other words, we are testing, are the mean scores of the proctored group less than mean scores of the non-proctored group, which is the same thing as saying, are the mean scores of the non-proctored group higher than the mean scores of the proctored group? Okay, that's step 1. Step 2, let's find the test statistic. Remember, because we have two means where the population standard deviations are unknown, we will be using the t-score. Okay, so let's go to our technology. This time we're doing a confidence interval test for two means. So we'll click on two means. We have a summary, so we'll click on summary. The sample size in group 1 was 30. This is the proctored group. The sample mean was 70.29 with a standard deviation of 22.09. The sample size of the second group was 32. The sample mean was 74.26, and the sample standard deviation was 18.15. Let's enter our data. We're doing a significance test. The null value will always be 0 for two proportions or two means. because the null value means that there is no difference between the two. In other words, mu1 equals to mu2. Now in this case, we're testing whether the scores of the proctor group are significantly less than the scores of the non-proctor group. So we will click on less. Okay, so our test statistic is negative 0.7703 and our p-value is 0.2222. Our test statistic t is negative 0.7703 and our p-value is 0.2222. So that leads us to our conclusion, since our p-value is greater than our significance level, which is 0.01. I wrote 0.05 by accident. But either case, we're going to, since 0.2222 is greater than 0.01, there's a high probability that this could have just occurred by chance, that the scores of the second group were higher than the scores of the first group. That could have easily occurred by chance, according to this probability. So we failed to reject the null hypothesis. There's not enough evidence to support the claim that the mean score of the non-proctored students is significantly higher than the mean score of the proctored students. The next example we will talk about in class. Now, for hypothesis testing for two dependent means, it's the same basic steps. Listed below are the number of words spoken in a day by each member of 6 different gender couples. The data are randomly chosen from a large data set. Use a 0.05 significance level to test the claim that among different gender couples, males speak more words than females. Okay, so in this case, we are not given a summary because since these are matched pairs, we have to list the data values individually. So what we can do is we can still go to our two means calculator because we have two different means. But notice we have two tabs, independent samples and two dependent samples. We will click dependent samples since we are talking about wives and husbands who are very heavily related. And we will enter the individual values for both samples. So for the first sample, I'm going to copy and paste the values. These are the words spoken by husbands. And then for the second sample, these are the words spoken by their respective wives. I will also paste. We have a significant test, null value is always 0. And what are we claiming? We are saying, do males speak more words than females? In other words, is the mean of the first sample greater than the mean of the second sample? Our test statistic is 2.5789. Our p-value is 0.0247. So our conclusion so our null hypothesis is that mu1 equals to mu2. Our alternate hypothesis is that mu1, the number of words spoken by husbands, is greater than mu2. Okay, so we list our test statistic, we list our p-value. Okay, so once again, our test statistic was 2.5789 with a p-value of 0.0247. Since the p-value of 0.0247 is less than 0.05, which is a significance level, we will reject the null hypothesis and support the alternate hypothesis that the number of words spoken by husbands, is greater than the number of words spoken by their wives.